The purpose of this video is to conclude our discussions of Chapter 10 through the explanation of analysis of variance. Analysis of variance, fondly called ANOVA by many, is used to determine if differences exist between means of 3 or more groups. So imagine, if you will, that having such a capability, of course, could be quite useful in a variety of fronts. So the ANOVA test is basically based on the t-test with equal but unknown variances, assumed equal but unknown variances, the one we did in 10.1. However, this one uses a new distribution called the F distribution. I think I mentioned this in class on Wednesday night. The F distribution is formed through 2 different sets of degrees of freedom. The F distribution, and I'll show you a picture of it here in just a second, uses this notion of a ratio of 2 different sets of degrees of freedom. So it is the ratio of the degrees of freedom of 1, which is in the numerator, and the degrees of freedom of the second group, which is in the denominator. And then we find our critical value, if you will, through this comparison, or this 2 sets of degrees of freedom, if you will. So this is a picture of a basic F distribution, and you notice it's kind of like a normal distribution, except for it's skewed over to the left side, and it's the same as other distributions that we have talked about in class. However, out of the right side of the tail, so kind of out in here, this is where our alpha would normally lie and where our rejection of the null will lie ultimately. Now, as you might imagine, because we've got 2 sets of degrees of freedom, the table is rather long. It's actually, I think, table 4 in your textbook, and it runs across maybe 4 pages or so. So just kind of keep that in mind, because that's the table that you would look up the values on, although a lot of the stuff we are going to do is actually, we're going to be able to do it in Excel. And just to be clear, here is just a piece of the table, if you will, where we've got the degrees of freedom set is 6 and 8. And so we find 6 at the top, the numerator degrees of freedom, and we drop down to where we find 8 degrees of freedom here at the bottom. And then we've chosen a 5% confidence interval, and so we would have the value of 3.58. So we would want to know if our area falls above that. That's all. So this is just a little quick example of what the table would look like. Now with ANOVA, we've got some assumptions that we need to be aware of. I don't always talk about the assumptions, but I think in ANOVA it's kind of important. So basically, the populations must be normally distributed. The population variances need to be unknown, but we assume they're equal, and that's kind of important. And then the samples are selected independently from each population. I mean, they're not like a matched pair design and all of those things we learned about with t-test. These are going to be independent samples. When we compare the total of the populations, we're going to use C populations rather than just comparing the 2 populations. Remember, that's the whole point of the F distribution, is that now we've got way more than 1 or more than 2 distributions we're comparing. We're going to do 3 or more. If we only have 2 distributions that we're comparing, then we just as soon use a t-test, because it's just simpler and much easier to explain, once we have our results. And the basic hypothesis for ANOVA is reflected here, that mu1 equals mu2 equals mu3 equals mu4 equals whatever up to mu c. And then the alternative is that mu1 does not equal mu2, does not equal mu3, etc. So we're just really looking to see if this group over here is equal to that group over there is equal to this group over here. And because we have multiple populations, now we're looking at something more like this, right? We've got groups that are all sort of overlapping, but we want to know if, this one is actually this one, or actually different from this one. The blue is actually different from the red, actually different from the green, actually different from the purple. Now here is a nice graphic depiction of the null and the alternative hypotheses. And here, this would be the null, right? Because here we assume that mu1 or x1 is equal to x2, equal to x3, x4. There's not a difference. And then the alternative is actually we're trying to show that, oh no, wait a minute, they actually are independent and different. And so here they're kind of split apart. So this is the alternative and this is the null. Kind of like this, I like to see it. So we're always trying to fight to show this. Because as you can see on the right, the population means differ, whereas on the left here they don't differ. They are equal. That would be the null. Now within ANOVA, it's important that you understand that we are going to measure several different things. Now, you are not going to have to do this by hand, but it is important that you understand kind of what is happening behind the computer program. So, first thing we're going to do is compute the amount of variability between the sample means. So between mu1, mu2, mu3, mu4, how much variability is between these different means. And then we're going to measure the amount of variability within each of the individual samples. So within mu1, how much variability is there? Which is of course different than the difference between the variability between mu1 and mu2 or whatever. So I'm going to let you think about that for a second, but I want to throw these terms out to you. So the between sample variability is measured with the mean square for treatments, MSTR. And this is an important distinction, right? That the MSTR, the mean square of treatments, so this is the variability between the various treatments, is one type of variability that we're interested in. And then the other type of variability we're interested in is the variability within the sample. So that's the MSE. So that's the mean square error within, say, mu1 or within mu2. It's not looking at the difference between the two groups. So from here, what I want to do is move to explanation through an example, because I always feel like an example just makes a lot of the stuff make so much more sense. So I'm going to use this example about these different forms of transportation. And then I will come back to this exact concept, this MSTR and MSE thing, because like I said, I think it's very important. And so I'm going to loop us back to this in a second. So what I'm going to do now is switch over to using Excel. I'm going to get the data that I've also provided right along with this, and that is the data to do the ANOVA called public transportation. So here's the example that I want to use. So it's based on an article that was published in the Boston Globe about commuters saving money while commuting using public transportation. So this guy claims that those in Boston have actually saved the most money of the various cities involved in this study. And the cities were actually Boston, New York, San Francisco, and Chicago. So because we have, these 4 different cities and they have different ends, we want to compare across these cities to see, which city, saved more money. So here I've just opened up the file of the, what is it called? The public transportation, and we're going to go ahead then and figure out, how much is each one paying, what's the average. So I'm just going to kind of quickly compute the average and the standard error for our group here. I'll just make some lines down here. I'm going to first insert in a column, and then I'll write out here the average. Yeah, we'll just go with the average for right now, just because then we can just kind of compare. So we just go up here, we select this, take average, and voila. And since this is money, my preference always is to have it in something that is like money. So on average, Boston savings is $12,622, New York is $12,585, San Francisco is 11,720, and Chicago is 10,730. So just in looking at it quickly, it appears that Boston has saved more money than the other states in public transportation costs. So we want to delve into that a little bit further. Of course, that's not going to be good enough for us to just say, oh, 12,622 is actually statistically different from 12,585. So we have to, proceed on then with our calculations. Okay, so what I wanted to do is show you how to come up with some of this stuff. So I have the data here. I've got Boston, New York, San Francisco, Chicago, which is just the way they provided it to me in the public transportation document. I created some totals. So I made the total of all of this whole thing. So that's just the sum of that whole box. Then I created the average of all by taking the sum and dividing it by n, which was just the sum of all the sample sizes. And then I created an average for each of these columns. So you can see that's the average, etc. Because ultimately what I want to do is try to figure out how much variability is between the groups. So the way I figure that out is by kind of this weighted average. So you see right here, I started typing it out, and I thought I would just show you kind of how I'm doing it. So I take 5, which is the n for this first group here from Boston, and I multiply it by the difference between the average for the Boston group minus the average of all, and then I have to square it. And I don't know why my 2 is not showing up here the way I want it to, but I did try this font and then superscript, but I don't know. It shows up and then it goes away. See it there? And then as soon as I hit equal, it'll go away. All right, and then I want to, so that's this first group, and then I could just copy this over and make it the second group, plus the third, because I got 4 I need to do. And let's just amend the numbers here. So this is going to be not 5, but the second group there will be 8. And then this third group here will be 6. And then we need to do one more. And this one will be 5. Now, of course, this is not going to be a working formula because I put this thing here first, but I just wanted to show you where the numbers come from. So I explained this first one. Please keep in mind that this is actually squared, even though it really doesn't look squared because of the way I can't get the superscript to work. All right, but the second one is going to be 8, and it won't be 12,662. Instead, it will be 12,585. So I need to change this, 585. And then this one here is 6. It'll be not 12,000, but actually 11,720. And then this last group down here is 10,730. And all of them will be subtracted by 11,990, and all of them will be squared. And so there I have made a working formula where I took the n, I multiplied it by the difference between this mean and the average, and then I squared it, plus this, plus that. Whoops, I guess my thing slid away there. There I've made the working mean to go with my non-working formula here. So now what I have there is the SSTR, or the amount of variation that I expect to see across, this sample to that sample to this one to the next one. And I've got it annotated here, and my value, if you will, is this 13,204,000, etc. Now I'm going to go about the business of computing the MSTR. In the same fashion, I'll write it out and then I'll do it as a formula. And so in a similar fashion, I've calculated the MSTR, so I take the SSTR that we just calculated, and then I divide it by the degrees of freedom. That gives us the MSTR, which is, it gives us kind of an average of the variation across the treatments. So these two sort of go together, if you will. Okay, and so then what I want to do is sort of build an ANOVA table together. Because of the importance of the ANOVA table, you absolutely need to understand what numbers go where in the ANOVA table and what is the meaning of the numbers. I'm not normally one to make you memorize stuff like this, but this is really important, and the ANOVA table is going to be in every bit of regression output you're ever going to do in your life. So it's important. So what I'm going to do is take these numbers that I've got here, and I've created an empty table in PowerPoint, and I'm just going to transfer the numbers over so you can kind of see how they fit. So the first line in PowerPoint, in an ANOVA table, is always the between group variation. So for us, the between group variation that we have just calculated is this big 13,000 or 13 million, the big number that we just calculated, 13,204,720. That is the between group value labeled as the SSTR. That gives us the amount of variation, the sum of squares due to treatments. So that's it right there. Our degrees of freedom are calculated as C minus 1 in this case. So for us it is calculated as 4 minus 1. So that's where I put that from. Now on this one here I didn't put the formula because it was a little cumbersome, but you know where that comes from. And then over here we have the MSTR, and the MSTR is the SSTR divided by C minus 1. So let's go ahead and write that here. All right, so I've gone ahead and added in a few things here. So we've got this first line here that's gray is always going to be between the groups. So this is the difference between the amount of savings for the people in Boston, New York, San Francisco, and Chicago. So it's between the groups, all right? So this is the first thing we calculated together on the Excel spreadsheet, and it is basically the SSTR, the sum of squares due to treatments. So this is the difference between the groups. This is the degrees of freedom. That is just C minus 1. So we had 4 groups, and we subtract 1 from that, then we get 3. Over here we have the MSTR, and the MSTR, just like we just did on the Excel spreadsheet, is the SSTR divided by C minus 1. So in our case it's 4,400,573. Now we're going to do the second group, which is going to be the within group. So we'll go back over to our spreadsheet and we'll calculate the numbers, and then we'll bring them in here so you can kind of see where they came from. The next one is the SSE, and the SSE is the sum of square error, which is the difference between the variance of the treatments. So basically what we're going to do is do n minus 1. So like for here we would have, I'm just going to grab this because it's just easier, copy, escape here, and stick this in here. So it'll be, now in our case it's not going to be n, it's going to be n minus 1. So essentially we'll have 5 minus 1 here, just to, you wouldn't have to write that, but just to, so you know where the number comes from. And then inside of here is just simply the standard deviation right there. Oops, we can't do that. We need to write the number out. So it's going to be, hold on here, it's going to be 87.79. And then we're going to square it right here. So we're going to do that and 2. And then after that, we will add to that the next one. So we'll do plus, and we'll have exactly the same thing again, except for now we got the second group there, which is New York plus Chicago plus, oh, San Francisco, sorry about that. And so then this one's not going to be 5 minus 1, it will be 8 minus 1, and then this one will be 6 minus 1, and this one, oh, I lost one of my parentheses there, will be also 5 minus 1. Okay, now we go back over here, and it's not going to be 87.79, it will be 82.23, 82.23. this one will be 50.05. Oops, 05. And this last one here with the same n will be 90.62. And I'm missing a parenthesis right here, so I'm just add that back in. Now this is not going to work, but I'll go down here and calculate the number for you. Okay, so I just calculated the SSE, and I did that by actually calculating the different values. So like this one here, I just did in -1 here. I did 5 minus 1, and then I just rolled it across and summed it at the end right here. Same thing. So the SSE then is 144,172. And now we'll go ahead and calculate the MSE, which is the mean square error. And we do that by taking the value we just calculated and we divide it now by, let me write this MSE. Now we're going to divide our value 144,180. We're going to divide this by N minus C, C being the treatments, right? So hold on, I got a typo here. This needs to be a comma. And so that would be 144,180 divided by 24 minus 4. I'm actually going to put this here and change this from 144,180 to the SSE. So you've got the notation for the process there. And then we'll calculate it right here. We got 144,180, and we're going to divide this by N, which is here, the total group, minus 4, the number of treatments. In our case, it's these cities, but treatments nonetheless. Now we're going to take this value and this value right here and go put them on our table. Oops, that one went crazy on me. There we go. So we've got our within groups row here, and the first number that we need to calculate is this business of n minus 1 times our standard deviation squared. Let's see if I can make that go. And we're going to do this plus and dot dot dot. So we're going to do this for all of our samples. In our case, we're going to do it 4 times. So let me just make that a little smaller. And then down here, we'll go ahead then and just put the value in. And for this one, it was 4,401,573. And then over here, we need to put in our degrees of freedom, which we're going to calculate as n of our whole process minus C. So for us, that is going to be 24 minus 4. And then over here for the MSE, that is simply the numbers divided by one another. So we've got, again, let me just put this little equation thing here. But not, we don't have the SSR in the numerator. Now we've got the SSE, so SSE. And we're going to divide it not by C over C minus 1, but N minus C. And that will be computed to come out as 7,209. But when I was just doing this, I noted here I didn't write MSE. No, actually it's not MSE, it's SSE. So I noticed I didn't write SSE, so I'm going to put that there. So you clearly know that this is the SSE in this one. This is the degrees of freedom, and then over here we've got the MSE. And the MSTR is here. And then up here I've got the same problem. I didn't give it its label, and it is the SSTR. And I'll make that just a little bigger so you can see it. There we go. Then from there we need to move into this last row down here, the totals. So the first total we put in here is the SSTR plus the SSE, which gives us this lovely number here of 13,348,000. And then we need to add this degrees of freedom column down. So I just went and gave these final numbers because I had left that off. So here we're going to do, I'll just put here for you, C minus 1 plus N minus C, which is going to be 23 in our case. And now the moment we've been waiting for is to compute our F right here. And F is computed, so this is the test value. So this is like our Z score, right? We're trying to get a nice big juicy number here so that we can reject our null. So here we take the MSTR and we divide it by the MSE. So I'm going to grab this formula here again, put it right here, and I'm going to change this so it says MSTR and MSE. And then I'm going to take it one more time, copy it, and put it here so that I can put the numbers in. So we've got the MSTR number, which is this one here, this 4,404,401,573. And we're going to divide that by our MSE, which is this number here, 7,209. And that is going to give us an F of 610.57. So if we were to use the rule of thumb that I had given you in class, and I said, you know, gosh, anything greater than 3 is perfectly sufficient, what do you think? Do you think there is a difference between these groups? Sort of looks like it. So of course that's the long way, but we got there. Now what I want to do is down here interpret kind of what we were doing. So basically we had the null hypothesis that there was no difference between the groups, and we want to determine if we can reject the null or in favor of the alternative that there is indeed a difference between the groups, or if we're able to reject it or not reject it. So first thing I'm going to do is write out the null hypothesis and the alternative, and then we'll talk about whether or not we can reject it or not. So there I wrote out the null and the alternative. The null is that the average for Boston savings for transportation is equal to all of these, and then the alternative is they're not equal. So now let's look at our F value to see what we do with this. Remember, we've got to look up our value in our F table there in the back of the book, and we've got to do this based on our degrees of freedom for the numerator and the denominator. So df num divided by dem. So our degrees of freedom in our numerator is 3, and then in our denominator is 20. Those come from right here and right here. So now I'm just going to go to my table and I'm going to look up degrees of freedom of 3 and of 20 to get the value for which I can reject or accept the null. So I just looked up my F value by going across the top to find 3. So it was whatever the third, fourth column over. The first column is the alphas. And then I came down the left until I found an N, or the other degrees of freedom number of 20. And I found that the critical value here is 3.10. So if our F test is greater than 3.10, we can reject the null. So let me just write that out. If F is greater than 3.10, we can reject the null. Thus, in this problem, we can absolutely reject the null, because I would certainly suggest that 610 is definitely larger than 3.10. So in this case, we will reject the null in favor of the alternative. So what does that say? It says basically that the groups are not the same. The groups savings are not the same. That's what it says. For all that, that's what it tells us. So now what I'm going to do is just walk you through this fast on using Excel. Of course, it will be much easier, but now you can kind of see the way all these numbers are derived. And again, like I said, this is very important. Okay, so what I did here was go ahead and calculate the ANOVA. Let me just show you how I did it. So I went into data right here, and then data analysis, single factor ANOVA. And then I highlighted all of my data here, and I didn't really worry that it didn't line up at the bottom. I marked labels. I was interested in 5%, and then I put my output range right there. So I hit OK. I'm not going to, because I just had done this, but see, you notice that we get this, well, we get a summary of each of the groups, right? It gives us the sum, it gives us the average, which is very useful. And then it also gives us the variance, which of course we could easily calculate the standard deviation from if we wanted to, because we needed that. But notice here, it gives us this table. Well, this is the same table that you're going to see when you do regression analysis. It's the same exact ANOVA table. I want to move that over so you can see it. So notice that our numbers are exactly the same as what we had just calculated in that other table. But now that we've derived it, we have a clue as to where these numbers all come from and what do they mean. And so if we think about this in terms that we can all sort of understand and get our heads around, you can think of the F critical value as something like the Z value. I mean, it isn't exactly the same, but it is similar in many ways to the Z value. And this number here, this 72,000, is kind of like our standard deviation for our whole sample or whatever. And when we divide it out, we get, this F value, which was a lot like our Z value. Here we've got the same critical value that we had looked up on the chart. And of course, we have a significant P value. So I'm going to walk you through one more problem and, kind of talk you through what you find. And then I'll let you try a few of these problems on your own. So I'm going to work for you this problem here about the Nike revenue. I believe it is problem number 45. Yes. So what we want to do here is first we want to set up our null hypothesis. And the null is always going to be, right, that the quarters that Nike is earning is not necessarily different. Because of course they want to show that they're actually different, but we're going to show that they're not actually different. So we'll first go up here to our tools, data analysis, ANOVA, single factor. And we need to extend this a little bit to there. We've got our labels. We want it at 5%, and then we'll put our output right here. That'll be fine. Here we've got our summary output, and let's clean this up here so we can actually read it. We're going to I'll put these into numbers. So these are our different groups. These need to be in date format, because otherwise we can't really tell what in the world we're talking about here. And then we've got an N and the sum and whatever. All right, and then down here, this is our ANOVA table that we are so interested in. So we've got this F critical value right here of 2.866. So now that is not going to be a clear, oh, absolutely, we're going to be able to reject the null, because that's, cutting it a little closer there. So we've got this critical value here of we need our F to be at least 2.86. That's the F critical value that Excel so graciously looked up for us. But our F value is only 0.64. So it looks to me like in this problem we will not be able to reject the null because our value is not significant, suggesting that these numbers, these averages, now let's just take a look at these averages and look and see if we think they look different. We've got 37, 33, 34. So they're evidently not different enough that we can indeed reject the null. So we are not able to say at the 5% significance level that the revenues for Nike do in fact differ across the quarters indeed. So this is problem number 45, I'm sorry. And from here, what I would like you to do are these problems, kind of a light week for homework actually, 45, 46, and 47, and then the case 10-3. All right, I hope you found this helpful, and I will see you soon.